Hey guys, welcome to my channel. In this video, I'm going to show you how you can class activation map on your model so that you can see which part your model is detecting in an image or making its prediction. So let's begin. So these are some of the libraries that we'll be using: OpenCV, PyTorch, NumPy, and some functions and methods within PyTorch and TorchVision. Next, we'll be using model equals to models.resident18. So we'll be using resident18 model for our example, and then we'll print it. If you want to use some other models, you can see the list of the models using this command. For now, let's run this. So as you can see, this is the model that we have printed, resident18 model. So in this, we'll be using the last convolutional network, the model, for seeing which part the model is focusing on for doing its prediction. So first we'll be putting the model in the evaluation mode. So model dot eval, and then we'll be defining a target layer. So target layer would be model dot the last convolutional layer of the model. So in this case, if you see, this is our model, and we need to go into the fourth layer, and within the fourth layer we have to go to the layer index 1, and within that we have to go to this layer. So we'll write model dot layer 4. Within that we have to choose the second index, which is 1, and dot on v2. This will be our target layer. So this is the image on which we'll be performing our operations. So in the next step, we'll be using one image which is located on this path. Then we'll open this image with the PIL library and convert this image into RGB, making sure that there are 3 channels in the RGB order. Okay. And next we'll be using the transforms function of PyTorch. So this will basically perform multiple operations. Like in this case, we'll be resizing the PIL image to 224 by 224 because that's what the ResNet18 takes in or expects, and then we'll convert it into a tensor, PyTorch tensor, with the channel height width format. Okay, and then we'll also apply one singular dimension. So for that we'll be using unsqueeze. So let's see the shape of the image. So in this case you can see the shape of the image. So using the transform library, we have converted the image first into channel height width format. So there are 3 channels since the image is of RGB. This is the height and width which is resized, and this is the batch dimension which we have applied using the unsqueeze function. Okay, so in the next step we'll be using hooks for capturing some vital information. So here you can see that list activation and gradient. So this will contain information regarding what features in the image were captured by a particular activation layer, and the gradients will contain the gradients of the output, gradients and weights of the output for different channels. So here we'll define a forward hook. The output will be appended to the activations, and in the gradients will be stored, gradients of the output. Okay. Target layer dot register forward hook, forward hook, and then target layer dot register full backward hook, backward hook. Contains information relating to which channel has captured which feature of the output image, and the gradient contains the weight of the output for each channel. So basically this will help us show that which channel is more important and which channel has captured more information basically. So after this we will be doing a forward pass and we'll print the shape of our output, and then we'll try to get the output for that class. So we'll be using argmax on the dimension 1. So this will give us the class index of the output, which will have the highest logits value, which is the raw value of the model. So let's see the output. This is the shape of the output. So it has 1 row and 1,000 columns. Out of that, the the index of the column with the highest value is 591. The value is 10.58. Okay. So after getting a forward pass, we'll be getting a backward pass now. So for that, we'll be using model dot zero grad. So normally what we do is we get we try to reset the gradients of the optimizer, but in this case we'll be using model dot zero grad instead of optimizer dot zero grad, because we want the gradient of the you know the gradient of the output. Hence we'll be doing model dot zero grad. So here we'll try to get the gradient of this dot backward. Okay. So as now we have registered the hooks and also done the forward and backward pass, the activation and gradients will now have some values in it. So we'll try to access it. So in this case we'll be only considering the 0th index, because the value that we need is stored in the 0th index, and we'll try to squeeze it to remove the singular dimension and detach it from the computational graph. Now let's print the shape of both activation and gradients. Let's see. So you can see both are of same shape, 512 channels and 7 by 7 of width and height. Now as you can see, the gradient is of size 7 by 7 across with 512 channels. So now what we'll be doing is we'll try to get the average gradient weight of each channel. Okay. And also we'll try to create a tensor of 0 values of dimension 7 by 7. So why are we doing this? I'll explain it to you in a few minutes. So for now, let's write weight equals to grad dot mean dim equals to 1 comma 2, since we want the average across height and width, and then cam, which is class activation map, equals to total zeros, activation dot shape 1 colon, which means we want only the dimension, the shape of the dimension, and the data type will be 32 to 32. Let's print the shape of the weights and cams. So you can see, since we got the average across each channel, the weight, the shape of the weights is 512, and the shape of the class activation map is 7 by 7. So in the next step, what we'll do is we'll multiply each weight with the corresponding channel in the activation. We are doing this since each activation or feature represents the details that it captures, and the weight represents the importance of each of the features. So we'll try to multiply each weight with the corresponding features captured by each channel, and then sum all of it. So for that, we'll write for I comma w in enumerate weights cam plus equals to w into act of I. So you can see weights have a dimension of 512, since there were 512 channels. So initially this was the weight tensor, and we had tried to get its average in each channel. So we have a tensor of length 512. Okay, 512 rows, and each element will then be multiplied with the class activation map, which is this. So the resultant output should have a shape of 7 by 7. Okay, so let's print it. You can see the resultant output also have the same shape, 7 by 7. Okay, this is a dummy tensor with shape 0 by 0, and now we have the actual class activation map. Then we'll apply ReLU on it to get rid of the negative values, since they don't, since it means that they don't capture any information, right? And then we'll try to normalize it by subtracting the class activation map with its minimum value and then dividing it by the maximum value. So these are the functions that we'll be performing. These are the actions that we'll be performing over here. Now, since this is a torch tensor, we'll convert it into NumPy. So basically this will show us where the model is looking when it's predicting a particular output. Next we will try to resize it, since if you remember, the shape of the class activation map was 7 by 7. So we'll try to resize it to 24 by 224, which is the size of our input image. Class activation map 224 by 224. So we'll rename it as cam. Now after converting a class activation map to NumPy and resizing it, we need to scale it back to 255, since we have normalized it, right? And if we try to visualize it, we won't be able to see a proper output. So we'll normalize it by converting it into converting it back to 8-bit integers to make it compatible with OpenCV, and there you go. And then after that we'll create a heat map where we'll be applying a color map. So we are doing this in order to get a heat map in colored format. Okay. Next we'll also be converting our original image to the size 224 by 224. Okay. So we are doing this so that we can overlay this heat map on our input image. Now to create an overlay, we'll have to impose one image over the other with with some form of transparency. So we'll have 50% transparency for both image and our heat map. So for that we'll be using this command overlay equals to cv2.add weighted image numpy 0.5 and heat map 0.5. Okay, so this is our image. This is 50% transparency which I was talking about. Same for heat map, and this is gamma value, which is a constant which will be added to every image. So this is done to, like, if you want to brighten up the image you can put some value in it, but in our case we have kept it to 0. Now finally we'll be displaying our image. Cam comma overlay and then cv2 dot wait key. So we'll be displaying it for 4 seconds. Let's see our output now. So you can see the red region represents what the model is looking at. So the blue area over here represents that the model doesn't look at those areas much, but the red ones are those which the model has focused upon to classify it. Okay, so I hope you found this helpful. Don't forget to subscribe. Thank you very much.